Good evening, everybody, and welcome to this inaugural lecture. My name's Ian Gordon. I'm the head of the college. It's my pleasure to introduce Professor Venugopal, who is the School of Engineering and the University of Edinburgh's Chair of Ocean Engineering. So Venki has had an education from across the world, his BTEC from Pondicherry University, an MTech from IIT Madras, his PhD from the University of Glasgow. I can attest the University of Glasgow is an excellent place to get a PhD from. That's a little bias I have, but don't tell anybody. Don't tell anybody else. Then research associate and research fellowships at Heriot-Watt University before moving further east still to come to the University of Edinburgh in 2005 as a lecturer and then working here since. As well as his chair, he's been the head of the Institute of Energy Systems, where he stopped that in 2023. And I know from speaking to various people in the school that he was a superb colleague and has been a much-loved leader in that role, as well as being hugely well-respected and recognized as a figure internationally in ocean engineering. So it's my pleasure to introduce Venki to give his long overdue inaugural lecture. Venki.
Thank you very much, Ian, for the kind and generous introduction. Good evening, everyone. It's truly a pleasure to stand before you tonight, to deliver my inaugural lecture. Are you able to hear me well? The backside, yeah, good. I want to extend my sincere thanks to everyone for being here, whether in person or online. I can't see too many people here, but Ed said there are people sitting on the other side. As Ian mentioned, I had the privilege of joining the university on November 1st, 2005. And when this November comes, I will mark the completion of 20 years in here. Tonight's lecture is going to be on the hydrodynamics of lazy wave power cables. And this is going to be on the hydrodynamics, not on electrical side. So if anybody is looking forward to listen to electrical components, I'm going to disappoint you. You can see from the PowerPoint on the left-hand side, you have the lazy wave power cable connected to a floating offshore wind turbine. And on the right-hand side, I'm standing next to an experimental cable model of the lazy wave cable in the flow wave tank. I look forward to sharing with you the research that I conducted with my team and myself. And let's see where we are getting to. Thank you again. So, if you look at my bio, it would say I was born in Pondicherry. If you are looking for where Pondicherry is, so you could see the red spot. This is within India, in the southern part of India. And just positive for a minute. India got its independence on the 15th August 1947. But Pondicherry was not with India at that time. It was with the French rulers. And the French handed over Pondicherry to Union India on, I think it's a November 1953. But even then, Pondicherry became a Union territory only later. Just about 1963, it became a Union territory officially. So the French was the language spoken there. And that's the reason this is the main city of Pondicherry. If you look at the street names, which will come up in a second, the names were very strange to us in those days. we were used to see the names, street names in our mother tongue or some other political leader's name. But this one says Bussy Street, Roman Roland Street, or something like that. So you could see the French impact there very clearly. So there is a I'm not sure whether it's clear from there, but that's where it is. Pondicherry is also a religious and cultural city. So we have churches, we have temple, we have mosque, and also nice streets. People can easily cycle there without crashing into a car. And as I said, temple. The temple is not just for human being to go and pray, it's also for the animal. You can see the elephant praying to the god. And if you watch carefully, these statues are elephant gods. We call Ganesh, Lord Ganesh, and you could see several of them carved in there. And the streets are popular for its color, vibrant color. The reason was, I think the Portuguese went there first, then the Dutch, then the Danes, then English, then the French. Then it became India. So Pondicherry is also popular for two particular places. One is called Arrowville. Arrowville is a universal town where, as the text says, men and women of all countries are able to live in peace and harmony. And on the right-hand side, what you see is the Aurobindo Ashramam, Sri Aurobindo Ashramam. Aurobindo was an independent fighter, and also he was a yogi. And he started this ashramam for various reasons. And later on, the mother, we call the mother, she's from France, Mira Alphaz, she joined Aurobindo, and then they started doing the servicing for everybody who wants peace, who needs peace. Right, I said I was born in Pondicherry. That's not exactly right. I was born in Pondicherry, but outside the Pondicherry, a village about 12 kilometers from the city center. And in here, I marked my house. And next to the house, you would see some green place. In my days, when I was a younger boy, that used to be coconut grove. So my father had something like 200, 300 coconuts planted in there. And that's where the place to go and play for us. And if you look to the right side, the open space, sandy beach. And again, 30, 50 years ago, it used to be much better, much cleaner. And now that seems to be not that beautiful it is, but it's still, you can imagine this. So this used to be our place to go and play. In my times, there were no TVs, no other things to play. It's just playing with friends. And what we would do, we'll just go to the beach in here. At just about 870 meters, it's marked here, and take a dip. The water would be very warm in the sense that 20 degrees, 22 degrees. So it's not like 16 degrees, 13 degrees we have here. So you can take a dip whenever you want, every day, all days. So again, in my younger days, as a teenager, I used to go there, sit alone sometimes with a book and watch the ocean. And I would find the waves crashing on the shore. And at that time, I don't know where they come from, why they are bigger, why they are smaller, why they break, and why sometimes they don't appear at all. Maybe that made me to study a course in ocean engineering later on. At this point, I needed to tell you something. So this person, he is a fortune teller, you can call him, or a palm history guy, palm reader. He used to come to our home once in a while. We don't know where he lives, or we don't know where he comes from, where he goes to. And one day, again, I'm that little, maybe 8 years, 9 years old, and he called me, and he asked me to show my hands to him. So because he's a palm reader. And looking at my hand, he said, so you are going to travel all the world. And here, so you need to imagine this. I'm a little boy living in a village. I've not seen an aeroplane in my own eye. So we used to spot aeroplane flying far, far distance, a little aluminum thing flying away. And if we spot one, then that would be our joy for 1 month or even year. We will say that I've spotted an aeroplane. Did you see it? Did you see it? That kind of chat with our friends. And this guy is telling me I'm going to travel all the world. I didn't believe him. But later on, it came true. I came to UK by aeroplane, and I traveled to other places by aeroplane. So that was true, in fact. The second thing he said was, I'm going to be clever and intellect. I didn't believe at that time. But anyway, even now, I leave this to you to judge. I'm not going to comment on that. And then the third thing he said was, I will be rich. I would be rich. That hasn't happened yet. Honestly, that hasn't happened yet. So to prove this, I have got this slide. So this slide shows you a poem with the lines marked on it. I don't want you to believe this, or if you want to believe it, or leave it. So the point is, there are lines marked on it: heart line, head line, marriage line, life line, fate line. So when I make a direct comparison, I could see the lifeline is stronger. You can't see from there, but I promise my lifeline is stronger. So my wife would be very happy because I'm going to live hundreds of years. And then if I look at the headline, kind of stronger as well. So maybe the palm reader was right. I am an intelligent. Then, the headline, then the heart line. It is also stronger and deeper. You can make a comparison if you believe in it. So that is also stronger. So maybe I will have prosperity in my life. And the little line there, that's marriage line. So if you count the number of lines, I have only one. So there is a proof. Wife sitting there. So there is one marriage line. And the bottom figure says money line, which is completely absent in my hand. Right? So he was wrong in there. I will never be rich. Right. So with this slide, I'm going to start my talk. There are so many people in my life and in my career. I needed to acknowledge them. And here is an opportunity to say thanks and acknowledge them. First of all, my PhD students and my postdocs. Without them, I wouldn't be standing here. And the mentors, collaborators, and friends, there is a huge list in there. Just to start with Alistair Borthwick, who is not with us now. He is become an emeritus. He was a very good friend. Just to say one example, I was deriving some sort of longer equation. And I got stuck with one formulation. I was referring to other books. I couldn't find a proper solution in there. So I went to Alistair's. He was sitting just opposite to me in his office. I asked him, Alistair, do you have a solution for this? Then he said, oh, yes, come in here. Then he pulled out an old file folder and handwritten mathematics equations and then give it to me. That's the solution, right? So he's that kind of person. And then I have stories to tell with everyone, including my old boss, Robin, sitting here, my new boss, Alistair's here, and so on. But I'm skipping everyone, considering the time. I'm going to Tom Bruce. Tom Bruce was in my interview panel. He asked not very difficult questions at that time. So I got this job because of Tom. And I have seen Henry, Gareth, and other colleagues. And also I'm happy to see David Stewart, and Marcus Mill sitting as well. Moving on to another list, I have Professor Vallam Sundar on the first name. He was the one who taught me how to write a journal paper. And then the other people here, Dr. Kamlesh Varyani, God bless him, he's no more. He was my PhD supervisor. And Professor Nigel Baltroff, a very clever man. He was also my supervisor. And Professor John Said, a very good friend of mine, a well-wisher, and he is retired. Unfortunately, he took an earlier retirement. I think he's on the team. I promised him an Indian lamb curry some time ago. That hasn't happened yet. And Professor Julian Wolfram, who gave me a postdoc position some 30 years ago. And Lars Johanning, my postdoc mate, let's put it that way. We both worked in the same office with Julian Wolfram. Now Lars is with Plymouth. Arne Ogler, a tall friend. He measured the largest waves in west of Hebrides, larger current in Pentland Firth and Orkney waters. And Professor John Chaplin, a great guy. And my another collaborator is Ching-Wei Ma from City University. And on the right-hand side, I have a list of people to thank. I'm not going to read out all the names. And I thank them very much. And finally, my thanks to EBRSRC and NERC, who funded the projects I applied for. So I don't write too many applications. I'm happy to say that. But whatever I applied, got funded. Most of them got funded. Okay, so the bio says I have 4 areas of research interest: tidal energy, wave energy, wind energy, and in coastal engineering. So the list here will tell you some of those, will cover some of those research topics. I'm not going to read it out, but it covers all the waves, winds, and tides. And recently I started working on machine learning applied to ocean modeling as well. And here is some of the research that we have done in the past. Probably I would say Robin would agree with me. We were the first to develop this kind of numerical modeling to propagate waves, to predict waves for the supergen projects that Robin used to run. And similarly, the tidal propagation in the Pentland Firth, and you could see the tidal velocity reaches sometimes more than 4.5 meters at some location. And similarly, in the previous slide, the wave height easily gets to 11 meters and 12 meters. It is significant wave height, not individual wave height. And with my students, I managed to do some experimental modeling of wave energy converters arrays, and same thing in the numerical modeling in a real ocean scale. So you could see placing a number of wave energy converters will remove the energy from the waves, and you could see what is happening to the coast after the removal of energy. We were also quite a bit involved with international research, and the one you see here is called the Sundarbans Biosphere. This is sitting between India and Bangladesh in the Bay of Bengal. And we had an opportunity to visit. And there is a slide showing Robin, David, and others who came with us, including the then British consular, the tall person standing here. And here is a wave prediction conducted for South China Sea. So as a part of another project. And if I tell you these kind of simulations will take very long time, months sometimes, if you want to generate a year worth of data or a year-long data. But with machine learning, that has become shorter. So Tian Tan is sitting here. She has done this work, wave current modeling. When you run a wave current model, coupled wave current model, it will take a long time to compute wave heights or any other parameters related to wave and currents. But we found out that applying the informer deeper neural network and the XGBoost machine learning makes the problem easier, simpler. You can do that in few minutes very easily. And another project, this is all just recently ongoing project. Munawir is sitting here. He has done this work. If you look into reports produced by Scottish government, and they say there is huge amount of erosion taking place in areas like Montrose and that kind of base area. So last year alone, there should be data showing here as 10-meter eroded into the oceans. So we wanted to find out why this is happening, how this is happening, and what is the reason behind it. So we done a modeling. The issue is there is a fresh water coming into the ocean, and that changes the salinity, it changes various behavior. And in here particularly, there is something called ebb tidal jet. That is the reason we believe that could be the reason for erosion in those areas. So the ebb tidal jet changes the magnitude and direction and volume of it changes with the wave height and also wave directions. So that's the red spot is the jet. So when we applied this kind of method to other locations where we have similar erosion, and those sites also have the same problems, similar type of ebb tidal jet flow. So this is an important issue. And just to cover two other recent work, car power wave energy converter. We have tested the survivability of car power wave energy converters in the flow wave and also by numerical modeling. And what we noticed is this. So initially, the device is supposed to do only the surging, move in one direction. But after some time, it starts moving laterally. It also sways. So you could see that it's starting this way now. And this is very important for the design of this particular wave energy converter. So this is called a transverse instability. And this is a function of wave period and wave height. It's not happening in all the wave periods. For example, if you look at the 1.8 seconds is a longer wave period, but the transverse instability is absent here. Whereas for other cases, it becomes bigger, smaller, and so on. So this is an important event or phenomenon the car power designer should consider. And we have also checked the survivability of motion wave energy converters. We have done the test in flow wave, and we have done the numerical modeling. So this is a motion wave energy converter. I must say I'm proud that one of the founder and managing director of motion energy converter was my PhD student, Cameron McNutt. And if you look into the slide here, there's this cable coming out of it. This is another example of application of lazy wave cable. Offshore wind sector. So on the right-hand side, there are two images showing you the floating offshore wave energy converters. We call them the semi-submersible type and spar type. And the literature says, or the report says, the wind capacity in operation by end of 2023 in Asia was 41 kilowatt, in Europe 34 kilowatts. So this is going up and up. If you look at only Europe, the topper is Netherlands. They produce 1.9 gigawatt. And next we are the UK, and then the rest of the countries. And if you specifically look at floating offshore wind, the Norway leads the queue, where they have 101 megawatt installation. The next to it, we are UK. and then the rest of the countries. So in here, what you see is a spar type floating wind turbine. It is not a monopile. It is a spar type. There are 11 wind turbines installed in the North Sea. The reason I put this image, these two concepts use the lazy wave power cable for power transport. So I don't need to repeat this, but the cables deliver the power produced by wind turbines to our homes and to other infrastructures. The cable cost itself 140 million for a 450 megawatt offshore installation. There are different types of cables used. One is called array cable, which delivers power from the wind turbine to offshore substation, and then the export cable, which delivers power from offshore substation to onshore substation. And within the array cables, there are two types, static cables and dynamic cables. So my research is about dynamic cable, which is what you see here. The dynamic cable, it's got a copper core and other materials in it. The typical weight would be 70 kilogram per meter. And the diameter, outer diameter, is about 140 millimeter for a typical 66 kilowatt rating. So 150 millimeter, it might look like only that size, but you can't. Can we go more than that? Or can we come less than that? We can't obviously come less than that. We can go more than that size. When we increase the diameter to larger sizes, there will be problems. That's what we called vortex shedding problems. So in here, a floater connected to a lazy wave cable, and on the right-hand side, the same thing, but I want you to pay attention to this image here. So there is something going on around the cable in the flow. That's what we call vortex shedding. So the lazy wave cable subjects to various loading. The load comes from wind, waves, current, gravity, and hydrodynamic lag, and also something called VIV loading. The motion of the floater also induces additional loading on the cable, and here it is listed. But one of the main reason for the cable failure is the vortex-induced vibration. In short, we call them VIV. Here is an image showing people repairing the failed cable. I'm not sure whether this is the cable failed by VIV, but it shows cable can fail, offshore cable can fail. Right, VIV is not only occurs for cables, it will occur for other structures as well, bridges, chimneys, transmission lines, aircraft, other offshore structures, moorings, pipelines, etc. And here is a YouTube video that shows you what is VIV is. We might have seen this somewhere, at least once in our lifetime, and we don't pay attention to this. But this is what the reason is VIV. And if you watch this one, it's really interesting. That is due to VIV. And I want you to pay attention to here as well, the bridge. And this one is stopping. It's not swaying. It's not oscillating. That's because of the presence of the. And this, I liked this comment. This is one of the YouTube comment. And this guy said, some engineers really screwed up. Right? That's not a nice word to you, but I put this here. It is not the fault of engineers. This is the environment that makes the cable to vibrate, the poles to oscillate. Right, so how do we connect this VIV to our research? So I'm going to talk about, or I'm going to mention two names. One is Reynolds, and at some point, we would have heard about this Reynolds number. We can't do air fluid mechanics or a fluid flow problem without including a Reynolds number. So this is defined here as a ratio between the ambient, U is the ambient flow speed, D is the cylinder diameter, and K is the kinematic viscosity. Very simple, 3 parameter makes one single number, which is Reynolds number. And the another number I want you to look at is the Vincent-Stoule, or Stoule number in short. So this is written as the ratio between vortex shedding frequency and to the diameter and to the incoming speed of the flow. So these two parameters are very important to classify or to define the vortex-induced vibrations. So if you look at the image on the left-hand side, we have a circular cylinder in plan view, and there is a flow, velocity u, coming onto that. So fluid mechanics colleagues, or if you have studied fluid mechanics, you would know what this is. So around the cylinder, when the fluid passes the cylinder, it develops the boundary layer. And within the boundary layer, there is a significant amount of vorticity present. And we also have another layer within the boundary layer called the shear layer. So the vorticity is fed into the shear layer. So if you can see both the sides, they are just separating from the cylinder. On the top, the vorticity will have a clockwise rotation, and at the bottom, the vorticity will have an anti-clockwise rotation. So they are rotating in the opposite directions. So what will happen when the Reynolds number, this is where I'm trying to link the Reynolds number to. The Reynolds number, when it reaches more than 40, these shear layer become unstable. And otherwise, within, let's go back and look at it again. So we have the shear layer, and we have the vorticity present. So the energy fed into the shear layer from the vorticity makes the shear layer to roll up. One rolling up at the bottom, another rolling up at the top. So there are two simultaneous rolling of the shear layer. And any disturbance to the flow, which happens for Reynolds number more than 40, will make the vortices unstable. So this causes one of the vortex to grow larger in size and in strength. Say, for example, the top one grows larger and bigger and stronger, whereas the bottom one, which has the opposite vorticity direction, stays smaller. So at some point, what will happen? The stronger vortex, this is we call vortex. Vorticity is the sort of swirls contained within the shear layer, but vortex is a single rolled up layer. So when the instability happens, it will roll into a ready-made vortex, and similarly you would see another vortex forming at the bottom. So the stronger vortex will try and attract the weaker vortex from the bottom. So this would pull the top stronger layer will pull the vortex at the bottom into the wake of the cylinder. And when this happens, the vorticity, which is opposite at the bottom, will cut off the vorticity at the top. So further supply of vorticity won't be available to the top layer. Therefore, the vortex will be shed and carried downstream. And when it disappears into downstream, there would be another vortex forming at the top, just close here. So this will be weaker, and the bottom one will be stronger. Then the process repeats. So the lower vortex will try and attract, will pull the smaller vortex at the top, and the vorticity is cut off. Then the vortex B also, or the vortex at the bottom also carried down. So this process repeats. It repeats with a particular frequency. So this is what we call vortex shedding. The shedding of vortex is called vortex shedding. You could see a Karman vortex state I've shown here in 3D view. So this vortex shedding, as I mentioned before, is a function of Reynolds number. Different Reynolds numbers produces different types of vortex shedding behind the cylinder. And as I said before, there is a relationship available between the Reynolds number and the Strouhal number. So you could see how they are related. So up to certain Reynolds number, they kind of keep a constant value, more or less a constant value, and there is a sudden jump towards larger value and comes down again. So this is a typical relationship that you would see for a circular cylinder. So the vortices, which I mentioned before, they won't be occurring in smaller scale, not just around the pole. It can happen over a large area. In this case, here is an island, and the cloud vortices are seen here. And we have also seen in our simulation, when we did the tidal modeling, you could see this is happening in water as well. So there is this vorticity. They are something like 40, 50 kilometer in size, not smaller in sizes. So that tells us vorticity is present, vortex shedding is present everywhere. In some cases, it vibrates the structure and makes the structures to fail. In these cases, you need to be careful where your tidal energy device is going to be, because the vortex will affect the energy protection. Right, there are a number of parameters that are linked with the vortex shedding, and I've given a large set of parameters here. The one to consider is the Reynolds number, the Froude number, Strouhal number, and reduced velocity, and so on. And the vortex shedding, which I mentioned before, they don't need to occur in single pair or in single units. They can occur as single vortices or in paired vortices, and also a combination of two vortices and one single. In here, a pair of vortices occurring on both the sides. In here, only one vortex is happening. In here, a mixture of vortex. So this is depending upon the velocity of the flow. And here you can clearly see that you can map the vortices into a combination of a pair of vortices, a single vortices, or two pair of vortices, and so on, with respect to the flow speed, or with something called reduced velocity. Now, another background I needed to tell you. So if you watch this plot here, so what is happening? The reduced velocity, which is a function of flow speed, diameter, and natural frequency of the cylinder, this is for a circular cylinder, is plotted. On the vertical axis, the vibration frequency F is divided by the natural frequency of the cylinder. So what happens here, when the VR ratio, this is a reduced velocity, when they are smaller, no vortex shedding occurs. Nothing happens. Then just about when VR reaches 4, somewhere here, the vibration begins. Vibration of the cylinder begins. And this line tells us the Strouhal number. There is a relationship. And if you make F by Fn equated to the Strouhal number multiplied by the velocity ratio, you would see this is falling on a straight line. So what's happening here? The vibration frequency of the cylinder starts from here and vibrating until it reaches a value of 5. At this point, it logs into the natural frequency of the cylinder. So it produces a constant line up to another value of VR, And this is what we call lock-in. So the lock-in is very important because that's the area you would see the cylinder vibrating a lot. So you could see when we plot the cylinder vibration with the cylinder diameter, there is a huge jump occurs only between the VR 4 and 7. Once it reaches 7, then the vibration frequency unlocks from the natural frequency and assumes the Strouhal number. For me, this is a very, very interesting matter because the cylinder vibrates and we think it will keep on vibrating, but it gets locked into natural frequency for some time and then gets released. This is an interesting phenomenon. This is what we call lock-in or synchronization. This occurs for a rigid cylinder in air. But if you do the same thing, same test in water, you can't repeat this. There is no lock-in, a clear lock-in. Instead, lock-in occurs somewhere else. It is not at the natural frequency, but it occurs at some other frequency. So therefore, when we did the test in flow wave, initially we were expecting to see this kind of test. When we didn't get this result, I wanted to blame Callum because Callum did the test. But it wasn't Callum. It wasn't flow wave. There is something reported already. When you do the test in water, you can't expect the lock-in to occur at natural frequency. And this is also a function of mass ratio. Mass ratio defines how stronger the cable would be. And in here, if you put a large mass ratio, stronger cable, then that phenomena we have seen before happens. It is almost locking into the natural frequency. But when we reduce the mass of the cable, which will happen, then this trend fails. The lock-in occurs somewhere else. And if you further reduce the mass ratio, if you make the cable lighter or the cylinder lighter, then it follows the Strouhal number. For a standard case of circular cylinder, the Strouhal number value is 0.2. It's locked. It follows the Strouhal number. So if you are expecting a lock-in that you would see in air, and if you measure the values in air, I wouldn't be applied to water. So that's the point I'm trying to get to. So now moving on to our own test. So keeping that in background and understanding the literature, we have built a cable model, and you might see a light blue color cable hiding in water. So that's our cable. And we constructed the cable with loads of difficulty. Tom Bruce kindly allowed us to do all this kind of initial testing and the waveflume. We had tried with various ways of constructing, making it stronger, making it lighter, and fitting strain cages inside because we wanted to measure the strain underwater. So these are all the strain cage wires that is coming out of it. So we managed to construct a 5-meter cable, and we fitted the buoyancy members that makes it to float, and we measured the motion of the cable in flow wave with the various wave current conditions, speeds and directions, and so on. So that's what I'm going to show you now. And here is another view of the cable underwater, and this is a measured profile with the Qualisys system. And we were able to reproduce the shape with a software called Arcaflex that is specifically designed to study the mooring lines or cable motions like that. But not yet. There are some problems. There are some models which we've seen is not reproducing the experimental results. Let's not go into this just now. So in addition to the cable which you've seen first, we call them mass ratio 1 We also went on to construct a heavier cable with another mass ratio just to see the differences. And here are the parameters. So we have run the current from 0.1 meter to 0.8 meters per second, and that gave us Reynolds number up to 24,800. And the Strouhal number, this is very important. The Strouhal number we measured for flexible cable is 0.12 to 0.14. But traditionally, the values reported for a circular cylinder is 0.2. We didn't get that value. There is a reason to that. Here is a setup. So when we put the cable into the water, this is how it looked. And here is a video that shows you the cable. So I want you to recall the video you've seen for the pole. The pole was doing sort of oscillation at a particular frequency. But if you look at this cable, there is no frequency kept. It vibrates randomly. Because the cable is flexible, its mass ratio is different. So therefore, the vibration, if you expect them to oscillate at a particular frequency, that doesn't happen here. It's a random vibration. And if you look at the cable underwater, and I'm showing the cable motion for 3 current directions, 0 degree to the cable, 90 degree to the cable, and 180 degree to the cable, the current directions completely changes the shape of the cable. So this is 180. It curls up everything. This is very interesting because the strain is going to be different. We have measured the strain on the cable underwater at 7 locations, which I'll show you in a minute. The strain at different locations are going to be changing. In some places, it will be very high, which will make the cable to produce high fatigue and maybe leading to a failure. So these shapes are important. And if you fix the velocity and the current direction, if you fix the current direction and change the velocity from 0.1 meter to 0.7 meters per second, this is also affecting the shape of the cable. This is important when they design the cable. When the industry design the cable, this is also important. The shape changes. They can't always assume this is going to take a lazy wave configuration. It will change. And the strain, which I mentioned before, the values of the strain changes. In some cases, these are all the 7 locations at which we measured the strain, one current velocity, another current velocity, higher current velocity, and so on. But you could see at lower current velocity, you get sort of a very defined time profile signals. But when you increase the speed, the signal is lost. It completely becomes highly random. And the same thing here. For different current directions, for different current speed, so when you increase the current speed, the strain becomes larger and completely chaotic. So we tried to analyze this to see what is happening here. And you could see for higher current speed, there is the energy transfer from one frequency to another frequency. And the shifting is going on between one frequency to another frequency. And that's what you see here. For some of the cases, for some of the directions, you would see kind of lock-in because the frequency stays at one value. And for other current directions, it doesn't. It changes the value. So what I'm trying to say here, it is a quite complex problem. And trying to find a solution in a uniform way is so difficult for us. And if you look at the profile, I'm showing the profile of the cable in X, Z plane, and also bird's eye view. This is the Y, Z plane. And the shape changes quite a lot, as I mentioned before, and it takes different shape for different current speeds. So we wanted to look at, there is something called inline motion or inline forces. The another one is the cross flow. So there are only these 2 ways you can define the motions and forces. But the cable is subjected to current from different directions and different speed. Therefore, which one is inline or which one is cross flow? Usually, if this is the cable the current direction is this, then the motion is in line. And if this is a cable, that's a cable, the current direction is 90 degree, then that's the cross flow. Or even for 0 degree, that's the 90 degree motion is cross flow. But with the cable going everywhere, it's difficult to define what is in line and what is cross flow. Therefore, we have made a transformation, applied this transformation, and managed to get the clear inline and cross flow displacement. So that's the displacement in the x direction, y direction, z direction for a particular current speed and at a particular location. I should say this, there were 36 markers fixed along the cable. So we measured the displacement at 36 different locations. And I'm showing the value for only one location. So for 90 degree current at the same location, you would see the x motion becomes stronger and the y motion becomes weaker and the z motion becomes stronger as well. So this is changing, the motion itself changing from direction to direction. So finally, we managed to resolve them into inline and cross flow direction, and that's the result you see here. And for other markers, again, they show very complex nature, and it is difficult to get a clear amplitude. Eventually, we got there, but at this point, we are not able to get. So this plot shows you the vibration amplitude, normalized amplitude vibration of the cable for different current speed. And each current speed gives you a different vibration. Usually, the literature says, when we normalize the vibration with respect to the cylinder diameter, you should get one single line, a defining line. But that's not happening in our case. And again, the literature says, if you manage to plot the inline vibration to cross flow vibration, example x and y coordinates, if you plot them, you should see a shape something like this, a clearly defined figure 8 shape. That happens in here for 3 different cases. This is coming from the literature, but this is what one would expect. But when we analyzed it, so here is a record, and we tried to make a similar plot between x and y displacement, but we didn't get the 8. And that's, again, we thought Callum is wrong.
It was my fault.
But he wasn't. But what has happened when we applied something called VMD analysis, virtual mode decomposition, and we found out there are 2 signals, F and G, and that's where the inline and cross flow vibrations are hiding. It is not visible in the total measurement, but they are hiding there. And if you use this mode 5th in both the cases, this is x displacement, y displacement, you take this one and take that one and make a plot, you start to see the 8 shape. So it is still there because it's a flexible cable, soft cable, not a rigid one, you don't see them directly. But again, there is another complexity. So these are all the shapes plotted for different marker location. The shape is not 8. Sometimes it is an 8. Sometimes it's an oval shape, a elliptical shape, sometimes sort of compressed ellipse. So this is again telling us at different locations, the cable is vibrating with the different modes. The amplitude is different. And therefore, you cannot apply a single A by D value or another simple equation to categorize its motion. So this is for 0 degree, and this is for 90 degree. When you send the current 90 degree to the cable, again, a complex motion. And another 180 degree. So there is no way of telling people that there should be an 8 based on this. So this tells us different locations will produce different mode of oscillation, different lock-in probably, and different shapes of trajectory. But in order to make sure that So we have constructed another cable. This time it is not a lazy wave, it's a simple catenary. This is a catenary shape. We just wanted to check whether the flow wave is giving the right answer or not. I'm not blaming the flow wave Tom. Tom Davies is sitting somewhere here. So that's a cable sitting in the catenary, and there are different current directions. And you could see there is some sort of uniformity. I want you to watch this one. This is doing like that kind of vertical motions instead of moving in the two directions. So then we separated out the inline and transverse, or inline and cross flow components for the catenary, and I superposed these two together, so maybe it's difficult to see, but the catenary profile gave us a very nice signal, very nice time series in all the cases. And when we started to plot the catenary motion, then you could see the typical figure 8. So after all, the flow wave was not wrong, and we were not wrong as well. So this is the cable that is producing different shapes. So that is important for the cable designer to bear it in mind. So we checked for other cases, other directions. It's again, the shape is clear. It is there. It is there. And the literature says one important thing. So when you have a figure 8 shape, and if you make a spectrum out of the signals measured, this is the cross flow spectrum, and this is inflow spectrum. If you watch the frequency component for the cross flow spectrum, I see this is about 0.3. The literature says this should be available in inline as well. And at the same time, additionally, you should see a double frequency. This is a typical case. So we managed to see this in all the cases. The cross flow frequency is repeated here. At the same time, there was a secondary peak occurred twice the major frequency. So that tells the experiments are right. That tells our analysis is right. And that tells we are telling the truth. And further, maybe I'll just considering the time, I'm just going to go a bit faster here. So with that confidence, we analyzed the entire data. And here we presented the data as a normalized RMS, root mean square displacement. I'm normalized with the cylinder diameter. And you could see they don't produce a simple jump like we've seen before. Rather than they just shows you an increasing trend sometimes. So this is for different marker location. So I was expecting to peak at one location and then comes down. The peak shows you the amplification vibration. That's not happening in here. And again, the same thing as I mentioned there for the catenary profile. When we analyzed the spectrum for the lazy wave, there are multi-peak suckers. There is not a single peak. So this is for a zero direction current flow. Multi-peak suckers, that tells me the cylinder being vibrated at multiple frequencies, not at one single frequency. And this is why, if we recall the video I showed you with the cylinder vibrating that way and then coming down and then goes up and then goes down. So that's because of it vibrates at different frequencies. And here again, the same thing for another current direction. Fortunately, at smaller current speed, we have seen a single peak of vibration, but then when you increase the current speed, the vibration goes. Sometimes you could see there is a vibration frequency. This is a vibration frequency normalized with the cylinder natural frequency, the cable's natural frequency. So you could see a ratio 17. So you would expect this to happen at 1, but it's not. It may happen at 1, it may happen at 2, it may happen at 4, it may happen even at 17 or 18. That's what it shows. So this picture shows you clearly the trend that we have observed before. So there is a frequency that can rise up to 18, 19 times the natural frequency of the cylinder or the cable. Right, so just one more minute, I'll be done here. So far what I've shown you is the pure current. The cable was subjected to pure current. And the video here shows you waves plus currents case. So we have added waves to that, and we have looked at the behavior of the cable with waves and currents. And obviously, we have noticed, as expected, the waves plus currents case produced larger amplification in comparison to the current alone case. So that tells me if the cable, if the wind turbine, floating wind turbine going to be in the water, where both waves and currents present, then the designer should consider the combination of both. We also measured the forces on the cable in 6 directions, and this shows the force coefficients, which are, these coefficients will be, if you believe them, and if the designer believes them, they are very useful for the designers. And finally, we have also attached the cable onto a floater, floating wind turbine, and we have done a good number of tests. And here it shows the video. The floater and the cable attached. The idea here, this is the real situation. The cable alone sit in a real ocean site. It has to be attached to a floating wind turbine. And when this happens, what is going to happen to the cable? So that's the analysis ongoing. Maybe if I have another inaugural lecture, I will provide all the details. And that's where I'm going to stop. Thank you very much.
Thank you, Venki. It falls to me to do the vote of thanks. My name's Alistair MacDonald, and I'm one of the very lucky colleagues of Venki. So first of all, thank you everyone here in person and online for coming today and celebrating Venki. Thank you for coming. Thank you to the college and the school for organising today. Like a lot of academics at the beginning of the talk, I was looking at my hand, looking at money, can't see where it is. As I went through, I started to realise that my lifeline maybe looks more like a lazy wave, I think, or a figure of 8. I don't know, it looks a little bit random. Now, there will be many of you that are intrigued, want discussion, and want to ask questions. The right place and the right time is to do that is outside. There are refreshments waiting for us, and we can continue to celebrate Venki. Last thing to say is for me to say thanks to Venki, both for your talk, intriguing as always, really enjoyable, but also thank you for being a wonderful colleague, a committed educator, and a really wonderful mentor to all those people that have been working with you over the last nearly 20 years here at the University of Edinburgh. So if I can ask everyone to put your lazy wave lifelines together, induce a bit of vortex induce vibration, and another round of applause, please.
Thank you very much. Thank you. Thank you. Thank you, Alistair. Thank you very much.